This joint work with my colleagues, Paul Duetting, Silvio Lattanzi, and Sergei Vassilvitskii. This paper is about looking at the classic secretary problem from the perspective of algorithms with machine learning advice. So the secretary problem is the most classic problems in online algorithms. You have this list of very well qualified candidates for the position of secretary, and then you get to interview them in random order. And your goal is to design a policy that maximizes the probability of hiring the best secretary in the group. From the online algorithms perspective, this problem was solved by Dinkin in 1963. And Dinkin showed that the optimal policy guarantees you probability 1/e of hiring the best possible one. The policy is actually very nice and simple. You wait until you've seen n/e secretaries and don't hire any of those. And then after that, choose the first secretary that's the best so far, that is better than anyone that you interviewed before. From modern perspectives, you can use machine learning to solve this problem. Let's say you collect a lot of data about this problem, train a very deep neural network, then you have a classifier that for every secretary, you can input the features of the secretary, and then get a suggestion, hire or no hire. And then you just follow the suggestion of the machine learning model. In the area of algorithms and machine learning advice, you want to combine these two perspectives. So imagine you succeeded in your previous exercise. You trained this classifier, it was a good one, but instead of using it directly, you want to design an algorithm that uses the advice of the classifier. So if you have this classifier, you can describe by two parameters called recall P and specificity P prime, which will tell you the rate of false positives and false negatives. Essentially when it says you should hire, when you should not, when you say you should not, when you should hire. And based on P and P prime, you see what's the best algorithm you can get. The competitive ratio is this expression here. The expression looks ugly, but let's try to parse it. Also, let me say also that's tight. That's the optimal bound you can get. So P is a probability. Let's imagine this plot on the right. Let's imagine P equals equal to P prime. So P is a probability that you get the correct advice, means hire when you should hire and no hire when you should not hire. In 1 minus P is a probability you get the wrong advice. So when P equals 1, your classifier is perfect. You should just follow this advice and you get competitive ratio 1. That's one extreme. The other extreme is P equals half, when the classifier essentially just says higher, no higher is half probability. In that case, a model you train is completely useless, but you can do 1/e by following Dinkin's algorithm. And I want to know what you can do in between, for P between half and 1. So to tackle this problem, we'll define a general model of secretary's advice that will allow us to go beyond binary classifiers. In that instance, an instance of this problem will be characterized by the following. There will be a signal space S, which you can think of the output of the machine learning model, and a joint distribution on n times S to the n. So a vector of D, a vector in D will be this two n elements. So the first n elements are 1 to n with the rank of the ith arriving secretary. And then the other elements will be the advice you get about the ith secretary. And we assume this joint distribution is known. So an algorithm is machine learning advice. For every I, we observe the partial order induced by the first I elements. So you don't observe the ranks directly, but you can compare. You can know who is rank higher than whom. And then you also observe the advice given by the model on I. And at that moment, the algorithm needs to either stop and hire secretary I or continue. And the goal is to maximize the probability of hiring the highest ranked secretary, so hiring the one that has rank n. Let me give some examples. So the basic setup is the setup of secretaries no advice. In that case, the signal space is trivial, so S equals 0. And the ranks are just a random permutation of n. And then, as you saw, there's a 0.36, so it's 1/e approximation. The second setup is the binary classifier, which described previously. Here, the signal space is yes or no, whether you should hire or not. The ranks are, again, a random permutation of n. In the joint distribution is what we described before, like so the probabilities are written here. So essentially, for the highest ranked secretary, it says you should highest probability P and not highest probability one is P. For every other secretary, it says you should highest probability one is P prime and not highest probability P prime. Third setup is this known as the IED stochastic version of the secretary problem. It's a very old algorithm. It was designed in 1966 by Gilbert and Mosteller. It's a very nice paper, and it shows that if you get this additional stochastic information, you can do better than just random modeling. You get 0.658. So in that setup, the signal space is R. And then for every secretary, you have a sample SI drawn IAD from some known distribution. And the ranks are the ranks induced by the signals. So R equals K if SI is the kth largest value among S1 to Sn. So that also induces random permutation. The ranks would be a random permutation, but they will be given by the SIs. And you have to observe SIs. So more recently, the non-IED version of this problem was studied, which is essentially the same problem, except that like SI is run from some Fi, which can be different. And this very nice paper by Sfandiari et al. Gave a 1/E approximation. These two previous setups are a special case of something called Markovian stopping. In Markovian stopping, again, the signal space is the real numbers, and the signals are generated from a known Markov chain. And again, the ranks are induced by the signals, as before. And this problem has applications in finance, has been like studying the many variations of that, studying the finance literature. I think this is a nice paper, 1988, called the Secretary Problem, Random Walk, and also more recent papers exploring variations of this question. And the sixth example that it's something that's very popular right now is this study online algorithms with samples. It is a model studied by Kaplan et al. And Correa et al. In this model, you get like n minus k numbers. It doesn't really matter what the numbers are, just n minus k distinct numbers. And the random subset of those numbers is given to the algorithm as samples. And the remaining n of them are presented to the algorithm random model. And your goal is out of the n elements, pick the highest one. It's not a priori clear how to phrase this as a problem as secularized machine learning advice, but then you can show that this is equivalent to the problem where the signal space is either 0 to k, and the signal SI is the number of samples worse than the current element. Right, so I just gave you 6 possible setups, and our main result is sort of give an algorithm to solve all of them, and pretty much any problem of that type. So our main result will be we give 2 conditions on the joint distribution D, called non-filtering and history independence. And I won't give you the conditions because it's hard to parse with a short time. But essentially what I would say is that all the previous examples in pretty much all the natural cases, they satisfy those conditions. You need to impose something to exclude like the signals encoding very complicated things. But essentially natural things like samples or binary classifiers, you can always encode this way. And under NF and HI. And at those, you can show the optimal policy is memoryless, so don't require remembering previous signals. And that the optimal policy can be computed from a linear program. And you can infer the approximation from the dual. To give you a flavor of how the proof is, I will first describe this linear programming formulation by Buchbinder, Join, and Singh from the original secretary problem. So what they did is the following. They look at the problem without advice, and they say that consider any policy, and then given any policy, let's define as variables Zi. So Zi will be the probability that you choose secretary I, conditioned on the fact that I is the best secretary so far. We'll be using that a lot, so let me just call that Ti. So essentially, Zi is the probability of picking I, conditions best so far. So a natural bound that you can get is the following. Up to time I, the probability that j is picked if the I is the best so far is at most 1, essentially because you can only pick at most one secretary. And then you can just write like the probability that j is picked conditional ti as zj times probability of tj conditional ti. And the nice thing is that probability of tj conditional ti doesn't depend on the policy at all, just like it's a number you can compute. It just depends on the fact there's a random order. This gives you an upper bound approximation ratio. You can write an LP that computes the maximum summation of the i's, probably that I is the optimal secretary conditional, it's the best so far, and subject to the constraints we just identified for every I. But it turns out that the very nice thing is that it's both an upper and lower bound. So what it describes that given a policy, we show how to compute an LP solution. But the opposite is also true. If you have an LP solution, you can also compute a policy with that their probability of success is the same as objective function. And the policy is simple. We just pick i's probability equals to zi divided by 1 minus the sum of j smaller than I, zj probability of tj ti. So essentially, we have an LP that fully characterizes the optimal approximation ratio, and you can derive Dinkin's algorithm by inspecting this LP. So what you want is to start from that formulation and try to incorporate machine learning advice. So that was a general policy, and this policy can be very complicated. This policy, now we are setting as advice. This policy can use the history of all advices obtained so far. And you again compute variables ZIS, which is similar than ZI, it's probably that I speak, condition I is the best so far, and you get advice S. Then you show that this satisfies an LP, that's now is more complicated. But it has a feature also that this constants AIS and CIS JS prime depend only on the distribution D. So you're left with this ZIS that characterizes the policy. And you can do as before, showing that if you have a general policy, you can come up with a feasible solution to the LP, and you can also go the other way. Given a feasible solution to the LP, you can derive a policy. But the nice thing is that if you do that, the policy you derive from the LP will always be memoryless. So you also always depend only on SI, on the advice you get in the current step, so you don't need to remember the advice you got so far, and on TI, which is being the best so far or not. It has the same performance. So under those two conditions that we identified, satisfy other problems we discussed, you only need to remember the current advice and whether it was the best so far or not. And you can also analyze a dual program. And out of the dual program, you can obtain the approximation ratio in the shape of the optimal policy. And even for cases that are complicated, like case samples, you can actually write exactly a closed form expression to what should be the approximation ratio. And also how the optimal policy should be via analyzing the dual. In many cases, the dual will also admit a greedy solution. So you'll be able to just solve the dual program by backwards induction. So induction from time n to back to I. In that case, the optimal policy will have a special structure called a threshold policy, which I'll describe in the next slide. So actually, I'll just give you an example. Here's a threshold policy for the binary classifier problem. A threshold policy has two thresholds, Ty and Tn. And up to Ty, you don't accept anything. So just interview secretaries, but don't accept. Between Ty and Tn, you accept if it's the best so far, and your classifier is telling you to accept. And after Tn, you accept anything that's the best so far. And you can see that both NP equals half, the optimal policy is Ty and Tn is equal to n over e, that's Dinkin's algorithm. In the other extreme, it's also essentially in that extreme, Ty will be 0, Tn will be n. And in between, you can also write a threshold as a function of p. So today, I presented a unifying view of multiple versions of the secretary problem. They gave you a way to write those problems in LP and also extract optimal approximation ratios and derive the optimal policies just from looking at LP directly. And also showed an example of getting LP formulation for non-problem extending to incorporate ML advice. And there's scope for doing that for a lot of other problems for which you have like approximation algorithms via LPs. Thank you so much.